In this video, I'm going to discuss Ampere's law. Now, this is the last one of Maxwell's equations. It's actually, it was first discovered by Ampere and then slightly modified by Maxwell. So let's have a look at what it actually means, and let's have a look at some different forms that represent Ampere's law. So in this video, we're going to discuss the integral form, which is stated over here, and then we're going to convert this into the differential form, which we will develop in a second. And how are we going to do that? Well, we're actually going to use Stokes Theorem. And Stokes Theorem is going to turn this equation over here into a differential equation. And it's going to have curl. This is all in vector calculus. So we'll get to that in a moment, but let's just have a look at a slightly simpler version of Ampere's law, or the Maxwell-Ampere Equation. Let's have a look at what it's actually saying. So I've drawn a little diagram to convey the physical meaning behind it. So let's have a look at this diagram. So this diagram shows a loop. It's a curve in 3D space. That's this red loop. Now the red loop has some directionality. So in this diagram, I'm trying to convey that this side is closer to us and this side is further away from us. And this curve acts as the boundary for a surface. And that's the blue surface. Now this is some kind of membrane you can think of that's being bounded by the boundary curve. And that boundary curve we're going to call C, and the surface we're going to call S. You can see in all of these integral equations, C is the curve and S is the surface. And C is the boundary curve of this surface. So you can think of the surface as a domain, and the boundary to that domain is C. Now, what are the types of integrals that we're dealing with? We're dealing with line integrals and surface integrals. Surface integrals are going to be over the surface S, and line integrals are going to be along that curve. So what line integral are we doing? We're doing the line integral of the magnetic field. And the magnetic field is the B field. Now, Stokes' theorem is actually stated here in some general field F. So this could be any vector field. And what we're actually talking about in Ampere's law is specifically the magnetic field, or the B field. And this little dl you can think of as, I'll draw it over here. dl is a tiny little, so this you can think of as an infinitesimal little nudge in the length. So that's dl. So this is a little l, and it's a vector quantity. And that little dl, what we're going to do is we're going to take whatever the B field is at that point. So imagine the B field is going like this way. This is the B field. That's the B vector. And this is a little arrow to describe the vector quantity. We're going to take the dot product of the dl with the B, and then we're going to add it up all over the curve. And why do we have this little circle here and here? Well, that circle is saying it's a closed curve. It starts, and then if you keep going along the curve, you're going to come back to the beginning. So the beginning and the end are the same thing. So that's what a closed curve is. And it has to be a closed curve because it's the boundary of a closed, it's actually not a closed surface, it's just a surface that is bounded by a closed curve. This surface is actually not going to be closed because if you think about it, it's just like a membrane of a drum. So imagine hitting a drum. The membrane is usually circular for a drum. If I draw a little drum, so you got a drum, and then you got the membrane. The membrane is like the surface, S, and the little edges of the drum that hold the membrane of the drum in place, that's the curve C. So now we have an intuition as to what this line integral is actually saying. This line integral is the circulation of the magnetic field. It's how does it spin around? So what causes magnetic fields to spin around? What generates spinning magnetic fields? Well, you can have two different things to generate it. So how can you do it? Well, Ampere discovered that currents can actually do it. And then Maxwell added this little term over here, which is analogous to Faraday's law of induction, where you have electric flux that's changing with respect to time, and that generates some circulation in the magnetic field as well. So a circulation of the magnetic field can either come about through current or through a change with respect to time of the electric flux. And the electric flux is this surface integral over here. Right? The flux through a surface is just going to be the dot product of this electric field vector. So imagine these are electric field vectors. At every point, there's going to be a little ds, which is going to be in the direction that's normal to the surface at every point. And we're going to take the dot product of those two guys, And then we're going to add them up for the entire surface. And that's going to give us the total flux through the entire surface. So the total flux through this entire surface is given by the surface integral. And that's what this capital phi with a subscript E is representing. It's the electric flux. But we're not just interested in the magnitude of the electric flux, we're interested in the change with respect to time. How is it changing with respect to time? If there's a changing electric flux, then you will have circulation around this loop. But if there's no change, then this term is going to go to 0. So what you can do is you can actually simplify this equation and get rid of that term completely if there's no changing electric flux. If you have just constant electric flux, or if the electric flux is 0, that's also constant. 0 is a constant. So this would disappear, and you just have this expression over here. Now, why have I written this surface integral as well? Well, you can actually write the current, right? The current is I, that's in amps. This current can be written as a surface integral of the electric current density, which is J. So J is kind of like the current, but it's the current per unit area, right? So how much current is coming through each little patch of area. And then it also has a directional component. It has a direction associated with it. And that's the direction of the flow of positive charges. So where the positive charge is flowing, that's going to determine the direction of this guy. And the magnitude is going to be determined by how much current is coming through each little tiny chunk of area. So if you imagine you've got current flowing, so if I draw a separate little diagram, imagine we have some kind of surface over here like this, and we take the surface and we split it up into tiny little surfaces like this, right? These tiny little areas. And each of these areas has a little bit of current flowing through it, right? There's a tiny bit of current flowing through each of these areas. So the current, the overall current would be all of these guys summed up together. So overall, there's a current, I, flowing in this direction. So positive charges are flowing upwards through this. This could be a cross-section of a wire. But this J guy, this guy is a vector that describes at each point how much, if we take the amps that are going through each point and we divide it by the little tiny infinitesimal area, we will get the value of J at every point. So you can think of it as J is a vector field that tells you where the current is flowing, in which direction, and it's telling you how strong the current is. And so it's natural to assume that if you take the surface integral over the entire cross-section of that wire, that's going to tell you all of the current. So this J is kind of like a vector that tells you what's going on at one point, and this current is telling you what's going on through an entire wire, or what's happening through an entire conductor. Right? Current has to flow through a conductor. So this cross-section, you can think of it as a wire, right? That's some kind of wire, and there's charges moving along here. And all the conventions are with positive charges, right? But we know, because of modern physics and quantum mechanics, that it's not actually positive charges that are moving in a wire, it's negative charges. It's electrons that are flowing through the wire. So the electrons are actually moving in the opposite direction of the conventional current. Now, why did we make this convention? Well, it's partly due to our ignorance of the microscopics, right? We didn't know what electrons were a few centuries ago. We just knew there was things moving around, and we just decided with the convention that positive charges are moving around. But it turned out that those charges were negative. It's not wrong, it's just as convenient, but it's slightly difficult to get your head around when you're first experiencing it. So that's this explanation, this little simplified version of the Maxwell-Ampere equation. So this is sometimes called the displacement current, right? It's got a slightly different personality to this current, but it's also there and it's contributing to the circulation of the magnetic field. So that was an attempt to kind of explain the intuition behind Ampere's Circuital law. Now let's take the integral form and convert it into the differential form. And that's going to give us some even deeper insight into what's going on. So what I've done over here is I've taken this current and I've turned it into that surface integral of the current density vector, J. And this flux term over here, I've gone in and turned that into the surface integral of the electric field. So we've got the flux and we've got the current. So keep in mind, anytime you see this, this is just current, and this is just the flux through the surface S. Now what we're going to do is we're going to use Stokes Theorem, and we're going to modify this equation. So we're going to modify the left-hand side. Now on the left-hand side, we see that we have a line integral over the boundary curve C. And that boundary curve C is the boundary curve of the surface S. So what we can do is we can transform this guy into this guy. We're going to transform the line integral into a surface integral of the curl. So let's go ahead and do that. So the left-hand side is going to turn into the surface integral over S of, we're looking at the curl of the B field. And then what we're going to do is we're going to dot it with ds. Okay, so that's what we've done. We've used Stokes Theorem, and we've actually turned the left-hand side into something that's more manageable when we're dealing with differential form, right? That's the first step. So make sure you're comfortable with that. We've turned this line integral into a surface integral of the curl. And if it's slightly confusing that this is an f over here, this is f because it's a generalized vector field. So this can work for any of these vector fields, whereas this is specifically the magnetic field, B. Okay, now what we're going to do is we're going to change the right-hand side. What we can do immediately when we see this derivative, we can differentiate underneath the integral sign. So we can move this, and when we move this inside here, it's going to turn into a partial derivative with respect to time. And what we can also do is we can, because you can see that this is the same surface S, we can combine this together into one big integral. And we can move all these constants inside as well. So let's go ahead and do that. So what we're going to have is a surface integral. And the surface integral is going to have mu, so I'll put brackets here. It's going to have mu naught times j, this current density vector. And then we're going to have to add to that mu naught times epsilon naught. And then what we're going to do is we're going to take, because these constants are going to come inside the integral, we're also going to take this derivative and put it inside the integral. And we're going to have the partial derivative of the electric field with respect to time. And then we're going to dot all of that with ds. Now, I want you to take a moment and let that sink in. So what we've done is we've moved all of the constants inside. We've taken the derivative over here and moved it inside, and it's turned into a partial derivative. And now we've combined these two separate surface integrals and merged them into one big surface integral because it's the same surface S. And when you have the same surface, you can actually combine surface integrals together. So what are we going to do now? Well, we have this guy is equivalent to this guy, and we can actually immediately read off something that is kind of fundamental. But before we do that, so what I'm going to do is I'm going to rearrange this and put this all into one integral, and then we'll do an implication. But what you can immediately see is that this is actually going to be equal to what's inside here. But before I go to that step, what I'm going to do is I'm going to combine this into one big surface integral by moving this to the other side and then smushing the two surface integrals just like we did before. So if I do that, what I'm going to get is this guy, the curl of the magnetic field, and then I'm going to subtract away mu naught j. I'm going to subtract away mu naught epsilon naught and this guy over here, the time derivative of the electric field, and that's all going to be equal to 0. So you can see all of this is equal to 0. Right, so what have I done? I've just moved this to the left-hand side, which is the result of that is the negative sign over here. This negative sign is a result of moving it to the left-hand side, or adding it, or subtracting the negative. So adding this with a minus sign to both sides is the same as subtracting it from both sides. And that's going to give 0 on the right-hand side, and on the left-hand side, we're going to get this. And just remember, you can always smush those surface integrals together if you have the same surface. And now what do we know? If the entire integral is equal to 0, that actually implies that everything inside the integral is also equal to 0. So then we know that the curl of the magnetic field minus mu naught times the sky minus mu naught epsilon naught times the partial derivative with respect to time of the electric field. That's all equal to 0. And what can we see from that? Well, we can just move these guys back. And you probably would have noticed that from here, but I just wanted to show all the steps to avoid any confusion. So in the end, what we have is the curl of the magnetic field is equal to mu naught times J, the current density vector, plus mu naught times epsilon naught times this partial derivative with respect to time of the electric field. Now it's got a similar form, doesn't it? It's got a very similar form to this over here. We've got something that's involved with the circulation of the magnetic field on the left-hand side. On the right-hand side, we have a term that corresponds to how much current is flowing. And we also have a term that corresponds to how the electric field is changing. Just this guy over here is concerned with one point, right? This is what's happening at one point. The curl is defined at every single point. So you have at one point, this is a curl vector. The curl vector is how is the magnetic field rotating around, right? It's a vector field and it might have some kind of rotation, might have some kind of circulation. So how is it circulating around? That's expressed in the curl vector. That's the left-hand side. This guy over here, this is also a vector quantity. And what it's describing is how is the current flowing at that single point, right? So it's the current per unit area at that point. And then this term over here, this is talking about how is the electric field changing. So anything that is creating a circulation has to either be a current or a change in the electric field. If the electric field is constant and there's no change in flux, then you're not going to have this term. So that displacement current term is just going to disappear. And you're only going to be left with this term. So when is the curl actually equal to 0? I'll just put a big box around this guy, because this is the final result. When is the curl of the B field actually equal to 0? When there's no currents and there's no changing electric fields. If there's no changing electric fields and there's no currents flowing, then the curl is 0. So there's no circulation in the magnetic field. So that is a condition that can occur if both of these terms disappear. So I'll give a quick summary as to what was covered in this video. At first, we talked about this form over here, which is the integral form of the Ampere law, or the Maxwell-Ampere Equation, which is also known as Ampere's Circuital law. Then what we did is we discussed this little simplified form over here, and we discussed the relationship between current and the current density vector, right? So it's a simple relationship where this guy is the surface integral of J. That's what the current is. And the units of this guy are amps. Those are the SI units for current. And this guy is going to be in amps per meter squared, which is the units of area. So per area, and then we're multiplying again by area when we take the surface integral, right? Because we're adding up over the entire area. So the meters squared, they cancel out, and we're just left with amps. So this is all in amps. But to make all the units match up, you might have noticed that there are mu naught and epsilon naught, right? The permeability and the permittivity of free space. So this guy's for magnetism, this guy's for electricity. Those are two fundamental constants. Another thing that you might also notice is that these two guys, when you multiply them together, they're actually the same as 1 over c squared, which is the speed of light. So that's another thing to note. We're going to talk about that in some of the other videos in this playlist. But overall, just remember, we used Stokes Theorem and a bit of manipulation of surface integrals to convert the integral form into the differential form. And if you want to go back from the differential form into the integral form, you just do the reverse, right? Do the reverse. Just take the surface integral of everything and then do Stokes Theorem in reverse to the way that we did it in this video, and you can actually get this form back. So I want you to think about this diagram, think about what the dl actually means, what the ds means, and think about what does it mean for a field to be circulating around, and what does it mean to have a surface that has a boundary which is a closed curve, and what does it mean for things to flow through that boundary, like currents and changes